Hello everyone from Math 2200, Discrete Mathematics. Professor Wenson here again with a video on your Zybooks section 14.3 titled Properties of Trees. Right, so you've been introduced to trees in section 14.1, saw some applications of trees, just a couple in 14.2. Now we're going to see some properties of graphs that are called trees. Alright, so the definitions for parent and child vertices in rooted trees make use of the fact that every vertex has a unique path to the root. There is, in fact, a unique path between any pair of vertices in a tree. So this actually this theorem was stated in section 14.1, and in 14.1 they said, oh, the proof of this will be shown later. Well, here it is. So the theorem is that there is a unique path, one and only one path, right, between every pair of vertices in a tree. And again, I like to let you read through the proofs on your own, all right, and see what you can make of them. Hopefully, you can understand and ponder them, and they make sense to you. So I'll let you read through that proof. But that is true. Take any pair of vertices in a tree, and there's going to be one and only one path between them. Right, so this activity here, for example, we got the two sequences of nodes given below, vertices, nodes, same thing. All right, notice when they say nodes, they also mean vertices. Given below denote the two distinct paths in the graph between vertices J and D. All right. So which of the following answers describes a cycle that you can deduce is in G? Right? Because remember, if there are two different paths between a pair of vertices, that means the graph is not a tree. Because in a tree, there's only one path possible between any pair of vertices. So yeah, if there are more than one path, if there's more than one path possible between J and D, that means the graph is not a tree. And if the graph is not a tree, that means the tree has a cycle. Right? The tree has a cycle. So looking at these, what could we deduce is a cycle in this tree? In fact, I am going to draw this out. I'll draw it out, and we can see what cycle we can see in the graph from these particular paths given to us. Okay, so here I've drawn vertices A through J in a nice circular kind of way. And now I'm going to actually I'll draw these paths that they gave us from J to D, right? These two different paths from J to D. So we have J to H, right? H to B, B to I to G, G to F, F to C, and C to D. So there's one path that's in this graph, right? They said that it's in the graph from J to D, and again, path means open walk, no repeated edges, no repeated vertices, as we've seen here. All right, now in a different color, I'll put this other path, also from J to D, and see if we can see any cycles that form, right? Because again, if there is a pair of vertices for which there's more than one path between them, then there's got to be a cycle in the graph somewhere. Right? It can't be a tree. So J to H again, right? J to H, right? That's the same edge, right? H to B again, right? So H to B again, just kind of lightly going over that. It's the same edge. B to A, right? B to A to F, F to E, E to C, and then C to D. Right there. Okay. Now, can we see a cycle in this? I can. All right. Now, there's lots of cycles. This isn't the only one, but look at all these edges, the red and blue edges that I have here. These all belong to the graph. So here's a cycle I can see in this graph. I can go from F to E to C, right back to F, can't I? Those edges are all in there. F to E to C to F. There's a cycle of length 3. So because I can find a cycle, right, that again tells me it's not a tree. Right, a tree has no cycles. And between any two pair of vertices, there's only one path. All right, now let's look at the options they gave us. How about B to A to G to I to B? All right, so I'll pull up my paper here. Hopefully you can see the paper. B to A. Now there's no A to G that I can deduce, right? So that's not it. B to A to F to G to I to B. B to A to F to G to I to B. Yep. There's another cycle. B to A to F. I've got that. To G to I to B. There's another cycle. A cycle of length 5. So that's the one I'll select. Now again, you could have just looked at these and listed, seen what edges were used and figured, which one of these has the actual edges from the graph from the listing instead of drawing it all out like I did. But, a drawing never hurts. I like making drawings. Right. Okay. All right. So now remember from section 14.1, the term leaf was defined in rooted trees, right, trees with that root and then the levels, as a vertex with no children. But if you're a vertex with no child, that means you have degree 1. All right, so they kind of extend that definition here now. So a leaf has a natural definition in free trees as well. Right? Now free trees weren't, like with that structure, they were just unstructured trees. So they extend the definition of a leaf, right? So instead of just having no children, a leaf of a tree is a vertex of degree 1. Right? And that's the way it is in a rooted tree as well, right? Every vertex that didn't have a child had degree 1, just one edge coming off of it. All right, and there is one technicality. All right? If a free tree if a tree has only one vertex, then there's no edges, right? So you can't say it has degree 1, but they'll still call that one vertex tree a leaf. But other than that, if you have 2 or more vertices, any vertex with degree 1 is going to be called a leaf. All right? And a vertex, another definition, lots of definitions in this chapter, I know. And a vertex is called an internal vertex if the vertex has degree at least 2. All right, so 2 or more. All right, so the following theorem gives a lower bound on the number of leaves in a free tree. So any free tree with at least 2 vertices has at least 2 leaves. I'm going to take you through a proof of this again. All right. It's a proof by contradiction. I'd like you to read it and hopefully you can make sense of it. But yeah, basically any tree you look at is going to have at least 2 vertices with degree 1. Any tree. Any graph with no cycles is going to have at least 2 vertices with degree 1. All right, as long as it has more than 2 vertices. Right? All right. So here are some examples of special kinds of trees. They're given special symbols, P subscript, S subscript. This is just a path of length 5. It's also a tree, right? There's no cycles in it. And this one's called a star graph on 5 vertices. Right? A path with 5 vertices, not of length. I said of length 5. I meant of 5 vertices. It's length 4, but a path on 5 vertices, a star on 5 vertices. Can you see the star, right? The heart of the star here, and then the points of the star coming out to these. But again, no cycles, and each of these has, at least 2 leaves. Right? This path here, this vertex has degree 1, and that end vertex has degree 1. Right? It has at least 2 leaves. This graph here has, 5 leaves. Right? S5, the 5 tells you how many points, how many leaves there are, how many points of the star. There's a 6th vertex in the middle. So here, this question relates to 2 classes of graphs. Right. The first class is a set of graphs which consist of a single path. So let P sub n be the graph that consists of only of a path with n vertices. So here's again P5, path with 5 vertices. The second class of graphs are called star graphs. Now S with a subscript, S sub k, consists of a single vertex connected by an edge to k other vertices, right? So it'll have k plus 1 vertices, like S5 here has 6 vertices. So a picture of S5 is given below. Is Pn a tree? Well, yeah. Right? There are no cycles. Remember, a tree is a graph with no cycles. If n is greater than or equal to 2, how many leaves are there in Pn? I just told you with P5 here, there's only 2 leaves. The beginning vertex and the end vertex. Those would be the only ones that have degree 1. Every other vertex in between would have degree 2, would be an internal vertex. So two leaves in Pn. How many edges are there in Pn? Well, let's see. P5 has 4 edges. And you can probably guess, P6, if I added another one, would have 5 edges. In general, Pn is going to have n minus 1 edges. Alright, so now let's look at these star graphs. Right? Is S sub k, so again, that's a vertex with an edge going out to, k other vertices. Is that a tree? Well, let's look at S5. Look, there's no cycles in here. So yeah, that would be considered a tree. How many vertices are in S sub k? Well, you see S5 here has 6 vertices. S6 would have, 1 vertex with an edge to 6 other vertices, so it would have 7 vertices. In general, S sub k would have k plus 1 vertices, right? K plus 1. And how many edges are there in a star graph with n vertices? So remember, if there are n vertices, that means it's S sub n minus 1, right? See, this has 6 vertices, but it's S5. So if you have n vertices, it would be S sub n minus 1. So there'd be n minus 1 edges. Right? See how S5 has 5 edges? There'd be n minus 1 edges. Okay, so again, hopefully easy enough. And then they talk about, a nice relationship between the number of vertices and number of edges in any tree. Okay. So let T be a tree, any tree, with n vertices and m edges. See, the number of edges is going to be the number of vertices minus 1. This is for any tree. Right? Take number 6 vertices minus 1, 5 edges. 5 vertices minus 1, 4 edges. Any tree. Right, well, there's not really a lot of trees in this one. But any tree has this relationship. Now they go through a proof by induction. So this section has a lot of things harkening back to our proof chapter. Proof by induction on the number of vertices. This proof up here was a proof by contradiction. So we're going back and looking at some old proof methods. So again, read through this. Hopefully you remember how to prove things by induction, what that meant. And make sense of this. But again, the number of edges will just be the number of vertices minus 1 for any tree. All right. Now finally, another definition, one final definition in this chapter. A forest. All right. A forest is a graph that has no cycles, but is not necessarily connected. Remember, a tree was connected. There were no separate pieces. That's a tree. That's a tree. That's a tree. But if you have multiple trees, disconnected trees, disconnected pieces, they're calling that graph a forest. All right, this is a forest with 3 trees, right? And the number of trees is, the number of connected components of the graph. So here's a forest with 3 trees. Now, a tree by itself could also be called a forest with 1 tree. All right, so this is any graph with no cycles could be called a forest. So every tree is a forest, right? But not every forest is a tree, right? This is not a tree. This is 3 trees, 3 separate trees. Okay, how many vertices are there in the forest? Well, let's see, there's 5 here, 3 there, that's 8. Plus 4 is 12. There are 12 vertices. How many edges are there? Remember, each tree, each individual tree, there are 3 trees here. The number of edges will be the number of vertices minus 1. So there are 5 vertices in this first tree, so 4 edges. 3 vertices in this second tree, so 2 edges. And there are 4 vertices in this last tree, so 3 edges. So you got 4 plus 2 plus 3, that's 9. 9 edges total. So again, it's really just, so what you're going to see is, you're basically, again, subtracting 1 for every tree that you have, because every single individual tree, the number of edges is the number of vertices minus 1. So you got minus 1 for this tree, minus 1 for this tree, minus 1 for this tree. So you see how it's 12 minus 3. Take the number of vertices and then subtract the number of trees, the number of components, and you'll get the number of edges in the forest. So for example, all right, so suppose there is a forest with n vertices and c connected components. It's a forest with c trees, c different pieces that are trees. So based on this example, what's a conjecture? I already told you. Give a conjecture, a guess, as what the number of edges in the forest would be. Well, it would be n minus c. It's the number of vertices minus the number of trees in the forest will be the number of edges. All right. Cool. Again, hoping this is a reasonably simple section. And all these sections in chapter 14 on the tree stuff been relatively simple. Just a lot of definitions, really. This section was nice again because you had some proofs that show you use some different techniques that you may remember, right? Proof by contradiction, proof by induction, and stuff like that. All right, and then you have your additional exercises. Right? Now, some of these are assigned, some may not be. Even if I didn't assign something, I would still recommend looking at it just to get more practice, more exposure. Try it out. And you got the solutions you can look at, but please try to work out the problems first. Try to do the best you can on your own first before you look at the solutions, right? Don't just copy solutions down without trying. You're not going to learn anything that way. And hopefully this video was a reasonable guide through this section. Of course, if you have any questions at all, send me a message and I'll get back to you as soon as possible. And thank you very much for watching.